project. And second semester, one from the project.
Hello everyone, I'm Mark Green and I'll be demonstrating or giving you a presentation on our wireless sound identification system. So the team members are from right to left, your right to left, Soontak, Back, Mitchell Miller, and Mark Schmiedel. So the projects we worked on, we had the intention of basically, we wanted to help the deaf and hard of hearing in their everyday life, just kind of making them aware of things. So say, car horn, door knock, things like that. Someone who's deaf or hearing might have trouble hearing it, while someone who has normal hearing wouldn't. So what we want to do is implement a system that would detect those sounds and notify them of it. So say you're at home, sitting at your computer and you have tea on the stove. It'll let you know that your kettle's whistling. So we want to do that. So to design our system, the first thing we did is we decided to split it into three subsystems. The first one is we had a wireless microphone to collect data. We had a central processing unit to analyze the data. And then we had an in-device system that is mobile, that can be carried around by the person, that would then notify them of the event. For the wireless microphone, what we wanted to do is we wanted to be able to have multiple sources. So given multiple sound sources, and this is also uncompressed sound sources, we would have quite a bit of bandwidth, so we decided to go with Wi-Fi for the technology. So for that, we used OpenThink's Flyport, which is made by Microchip Technologies. And it basically has a PIC microcontroller and a Wi-Fi module. So the PIC microcontroller has an ABC on it that samples the audio, and then the Wi-Fi module then transmits it to be processed. So for the central processing unit, we decided to use a PAN board. The PAN board uses an OMAP4 on it, so we found that that was more than sufficient for our processing needs. It also has a Wi-Fi chip on it for receiving the audio signal, and to communicate with the in-device networks, we used a serial data out of the USB to communicate with that network. So once we got the audio data, we used a SOLAR algorithm, which was developed by some students at Carnegie Mellon. And the way it works is it describes sound events by using certain statistics of the, so basically we'll pass the sound files to train it. You pass it positive files and negative files. In each sound file, it classifies it by statistics such as it will take the mean power within a frequency band, the standard deviation of power, things like that to classify the sound. And what we'll do is we'll have it running in real time, and we will take the classifiers of the sound received from the microphone and compare it to these known classifications. So once the PAN board detects an event, it will then send it out serially through the USB to the device. So for the end devices, we decided to use a Zigbee network and MSP430. So we'll have a MSP430 plugged into the USB of the PAN board, and we have a serial communication channel there, and we can send events there. Once it sends the event to the MSP430, it will then broadcast it over Zigbee, and the end device will then display the notification, and if we also want to have it vibrate on, it will also vibrate to notify the event. So that is our system. Any questions?
Mark, how many frequency bands do you look at?
So right now we have 16 bands. It's
16?
Yes. So it's configurable. We decided to use the ones that Solar recommended, which goes from 200 hertz to 4 kilohertz, and mostly in the low frequencies you have denser bands.
How are the frequency bands on space? Equal space? Or?
No, they are based on what?
Pardon me?
They experimentally is how they determine the bands. So I think like the first one's like 200 to 240, then 240 to 300. Typically they get larger.
Are there like logarithmic basis or?
It's completely experimental, but it's follows the pattern.
Experimental by?
By the people who developed the solar algorithm at Carnegie Mellon. They did it based on what they found to be most accurate.
The TV's on, baby's crying in one room, kids are fighting in the other room, somebody knocks on the door, can't figure that out.
So that's actually why we want to do multiple microphones. So, I mean, for one thing, if you have a microphone and say the living room, it probably won't hear the door knock very well. So based on where the microphones are, we will be able to determine kind of where the sound is coming from. In fact, we have a naming mechanism so that when it actually you get your notification, then it'll say maybe like living room, baby crying, for example. You have a question?
How far along are you?
So we pretty much have it all implemented. We're running into a couple problems. We have solar implemented on the panel board, and it's actually running very efficiently. We can handle about 20 sound sources. But one of the problems is that we need to train it more. So we're having problems within actual sound environments accurately detecting events. That being said, the actual hardware is implemented. The only other thing we need to do is train the software.